In this video, we discuss basic differentiation rules. So basically, we've got this limit definition of the derivative. Well, actually, two limit definitions of the derivative. We know that f prime of x is defined to be the limit as delta x approaches 0 of f evaluated at x plus delta x minus f of x divided by delta x. And this is just the slope of the secant line between x delta x, or excuse me, x f of x and x plus delta x f of x plus delta x. And then we just let the 2 points get closer and closer together, which is the same as saying delta x goes to 0. That's the definition of the derivative. Actually, applying that definition of the derivative can be kind of a pain, especially if our function has a lot of terms. Let's say we had, f of x equals negative 2x to the 5th plus 10x to the 4th minus 3x cubed plus 7x squared minus x plus 2. Applying that formula here is a pain because if I evaluate f at x plus delta x, look what happens. We end up with 2 times the quantity x plus delta x to the 5th plus 10 times the quantity x plus delta x to the 4th, and so on. It sort of just gets very complicated looking relatively quickly. We have 7 times x squared, which is, we're replacing the x with x plus delta x. If we do this and we simplify and then we subtract the original function f and then we factor out the delta x, take the limit as delta x approaches 0, we're going to get the right value for the derivative of this function. But it's much easier if we can come up with some shortcuts, some basic differentiation rules that will allow us to find the derivative of a constant times x to some power every time, or a sum of polynomial terms like this one. So this lesson is about sort of trying to avoid this scenario. If I wanted to evaluate this x plus delta x to the 5th, for example, I'd have to draw Pascal's triangle, go down to the 5th row, find the coefficients of x plus delta x raised to the 5th, expand that, and then I'd have to do the same thing for x plus delta x raised to the 4th, and x plus delta x cubed, and x plus delta x squared, and it's just tedious. It's not difficult to do. It's relatively easy, but it just takes a really long time. These basic differentiation rules will allow us to avoid that scenario. In a couple of cases, we will use this definition to derive our formulas, but we'll also rely just on our geometric intuition and understanding of the functions themselves. So that's the plan. Trying to avoid doing this every time by coming up with some basic rules. So here's our first rule. It says the derivative of a constant is 0. And I think it's really easy to understand. If you have y equals a constant, y equals 3, and you're asking yourself, well, what's the derivative of that? Well, obviously the slope of y equals 3 is 0. The horizontal line has a slope of 0. So we would write y prime equals 0, which is the same as saying the derivative of 3 is equal to 0. So I might write it like this. But when I see that symbol, that derivative with respect to x of 3, I'm thinking of the line y equals 3, and I'm thinking to myself, well, that has a derivative of 0 or a slope of 0. And then the same is true here. This is the derivative with respect to x of a constant times x. Well, if I graph a constant times x, that's just a line with that constant as its slope. So let's say I have y equals 3x, and that's just a line that passes through the origin and has a slope of 3. So we start here and we go up 3 and over 1. And then we graph that line and we say, well, what's the slope of that line? Well, we know that the slope is 3. Now we could use the formula to derive these expressions if we wanted to. But if x is here and x plus delta x is here, think about it. F of x plus delta x is 3. F of x is 3. So we just end up with 3 minus 3 divided by delta x. So we have 0 divided by delta x, which gives us a 0. So it's really not necessary to apply that rule, apply that limit definition of the derivative here, but we can, and we'll get the same result that we would get by just looking at the line and saying that's a horizontal line. Of course, the slope is 0. So we've got a slope of 0 there. And then here, if I replace x with x plus delta x, I have 3 times the quantity x plus delta x minus 3x I would just simplify, distribute the 3 to the x and the delta x, reduce like terms, and then you'd end up with 3 delta x divided by delta x, which would give you a slope or a limiting value of 3, which is exactly what we get when we look at the equation of the line and we say, what's the slope, what's the derivative of, or what's the slope of a linear function? Y equals mx plus b has a slope of m. We know that, we've learned that before, so we know that the answer is 3. Now this one is a little bit more complicated. It turns out that the derivative of x to some power is that power times x to the 1 less power. So for example, the derivative of x squared is 2 times x to the first. So I bring my exponent down, and then I multiply by x to the 1 less power, and that's going to give me the derivative every time. Now we can derive that formula using the limit definition if we want to. Let's take the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x for f of x equals x squared. In that case, f of x plus delta x goes right here, and f of x, which is just x squared, goes right there. Now remember what f of x plus delta x is. F takes its input and it squares it. No matter what you give me, if I put it into this function, the output is that input squared, provided that the input is in the domain. Let's say we're taking x plus delta x and we're substituting that in right there. So that is the expression that goes right there. So going back to this expression here, we say that limit is equal to the limit as delta x goes to 0 of x plus delta x squared minus x squared all divided by delta x. We write that twice in FOIL. First times first is x squared, outer times outer is x plus delta x, or x times delta x, excuse me. Inner times inner is just like it, so we got 2 of those. Last times last is delta x quantity squared. We're subtracting x squared. And we notice that we've got an x squared and a negative x squared term, so those terms reduce. And we also notice that this term has a delta x as a factor, and this term has 2 delta x's as factors. So we can factor the delta x out. Delta x times 2x gives me this term. Delta x times delta x gives me delta x squared. It's still a 0 over 0 indeterminate form if I substitute in delta x right now. But if delta x is non-zero, and we're assuming it's non-zero because we're taking the limit as delta x approaches 0, and delta x isn't actually equal to 0 when we compute the limit. It's just a positive or negative number divided by itself, which is 1. So now we say to ourselves, is this function 2x plus delta x continuous at delta x equals 0? And it is. So the 2x is just a function of x, and delta x can be replaced with a 0. So we get 2x. Now, if you are computing this limit definition in general, for f of x equals x to the n, it's a little bit more complicated. Actually, I should label this. This is f prime of x equals f for that particular function f. For this example, we have f prime of x equals the limit as delta x approaches 0 of f evaluated at x plus delta x minus f of x all divided by delta x, which is equal to the limit as delta x approaches 0 of x plus delta x raised to the nth power minus f of x, which is just x to the n, all divided by delta x. Now, to expand this, it's helpful to know the binomial coefficients and how those work. The binomial coefficients really depend on the value of n. But we know basically what the expansion is. The first term is going to be x to the n. The next term is a constant times x to the n minus 1 times one of the delta x's. The next term is another constant times x to the n minus 2 times delta x squared. And we keep going like this. The powers of x keep decreasing. So we have x to the n, x to the n minus 1, x to the n minus 2. Eventually, for our last two terms, we're going to have an x and a delta x raised to the n minus 1. And then finally, a delta x raised to the n. And there's a coefficient out front. And those coefficients can be found using Pascal's triangle if you have a particular value of n. But they're just numbers. Now I want you to notice that if we substitute this expression in with particular numbers here and here and here, when we subtract the x to the n, that term reduces with that. And you're just left with a bunch of terms that all have a delta x as a factor. We've got delta x, a delta x squared, delta x cubed, and so on. Eventually we have delta x to the n minus 1 and a delta x to the n. And we can factor out a delta x from everything. So this expression right here I didn't have enough room, so I had to add the limit on the second line. Now again, I want you to notice the pattern with this. We've got x to the n, x to the n minus 1, x to the n minus 2. All the powers of x reduce as you go from left to right in each term of this binomial expansion. And the powers of x to the n, or delta x to the n, actually reduce or decrease as you go from right to left. So we end up with a delta x to the n over here, then delta x to the n minus 1. The next one would be delta x to the n minus 2. Eventually you end up with a delta x squared, a delta x to the first, and then delta x to the 0, which means there are no delta x's there. So that always happens. And then we have particular coefficients here and here. Well, and for all of these terms in the middle, that really don't matter except for that first one. That first one's really going to matter for. So I just want you to notice. Oops, that last term is that delta x to the n is from here, and we subtract the x to the n. So I have a delta, or an x to the n divided by delta x there, minus x to the n divided by delta x, so those guys reduce. Then I've got a delta x in common for all of these factors. So we end up with something that looks close to this. And since delta x is a common factor in the numerator and denominator, those reduce. And we just end up with this expression. Now notice, for this first term, we originally had a constant times x to the n minus 1 times delta x. We need to figure out what that constant is. After factoring out the delta x and reducing it, we just end up with that constant times x to the n minus 1 here. Now, and then every other term on this list has delta x as a factor. Because this term started out with a delta x squared and we only factored out one delta x. This last term started out with an x to the delta x to the n. So when we factor out one of those, we're left with x to the n minus 1 of those. So when we take the limit as delta x goes to 0, this term goes to 0, this term goes to 0. All of these terms go to 0, with the exception of this guy right there. So the answer for the derivative of x to the n turns out to be that constant that's multiplying x to the n minus 1 in the binomial expansion. So we're focused on this second term in the binomial expansion of x plus delta x raised to the n. Now let's see if we can't find a relationship between this coefficient and n just by pattern matching. The one way that we can do that is using Pascal's triangle. We start with a 1 and then 2 ones below that. And we always have ones on the outside. And then we add these two digits to get this number here. 1 plus 1. We bring the 1 down and then we 1 plus 2 is 3. 2 plus 1 is 3. And then we have a 1. And then we've got a 1 and then a 1 plus 3 is 4. And a 3 plus 3 is 6. And a 3 plus 1 is 4. And then we've got a 5, a 10, 10, a 5, and a 1. Then a 1, a 6, a 15, a 20, a 15, a 6, and a 1, and so on. These are the coefficients. Of, well, let's say a plus b raised to the n. Now, depending on the row. So these are the coefficients of a plus b squared. These are the coefficients of a plus b cubed. These are the coefficients of a plus b to the 4th. These are the coefficients of a plus b to the 5th. These are the coefficients of a plus b to the 6th. And so we're looking for a pattern, a relationship between these exponents and these coefficients of that second term. So when I have an a plus b squared, I've got a 2 for my coefficient of my second term. When I have an a plus b cubed, I have a 3 for the coefficient of my second term. An a plus b to the 4th, I've got a 4 for the coefficient of my second term. So notice that the exponent here and that coefficient match. So if that's an n, that's also an n. That tells me this is going to be n, which means that this is n, which means that this is n, which means our rule gives us the derivative of x to the n is n times x to the n minus 1. Now, if you're still curious about these coefficients, you can think of it this way, or well, not, how do I say this? If you're still curious about how to use Pascal's triangle to write down the expansion for each of these, it's relatively easy. Let's look at this example right here. Let's say you've got a plus b raised to the 4th. Well, the degree of each term is going to be 4. So we start with an a to the 4th, and then we're going to have a coefficient times a cubed times b to some power plus a coefficient times a squared times b to some power plus a coefficient times a times b to some power plus b to some power. So a to the 4th, a cubed, a squared, a to the 1st, and no a's. And then as we go the other way, we're going to start with a b to the 4th, and the powers of b are going to decrease. So we'll have b to the 4th, b cubed, b squared, b to the 1st, and then no b. Then the coefficients that go here, here, and here come from this expansion. So you're going to have a 4, a 6, and a 4. So if I wanted to, could use a concrete example. Let's let f of x equal x to the 4th. The derivative of x to the 4th is the limit as delta x goes to 0 of f evaluated at x plus delta x minus f of x all divided by delta x. So we end up with x plus delta x raised to the 4th power. So we're taking this expression, we're substituting that for x, and then we're raising it to the 4th. And then we're subtracting x to the 4th, and then dividing by delta x and taking the limit. Just using this pattern, we've got x to the fourth plus 4x cubed times delta x plus 6x squared times delta x squared plus 4x to the first times delta x cubed plus delta x to the fourth minus x to the fourth, all divided by delta x. Again, the 4, the 6, and the 4 come from Pascal's triangle. And then the way I know the powers of b, a simple way to remember it, is the degree of each of these terms has to be this degree. It has to be 4. So when I see that a cubed, I know I need 1 more b so that the total degree is 4. If I have an a squared, I need 2 more b's for the total degree to be 4. Here, if I've got 1a, I need 3 b's for the total degree to be 4. And of course, we've got the b to the 4th on the end. So these guys reduce. And then we see that all of these have a delta x in common, so we factor that out. These guys reduce. And its delta x goes to 0. This goes to 0, this goes to 0, and this goes to 0. And we just end up with a 4x cubed. Which is the same answer that we would get if we just brought the power down and multiplied by x to the 1 less power. So if we're just applying that rule, the derivative of x to the n is n times x to the n minus 1. The derivative of x to the 4 is 4 times x to the 4 minus 1, which is 3. Derivative of x to the 10 is 10 times x to the 10 minus 1, which is 9, and so on. So it's a very easy rule to apply, but it comes from these expansions and that coefficient. And we were able to just infer what the relationship should be between that exponent and the coefficient by looking at that second coefficient and that second sort of diagonal in Pascal's triangle. All right, so that is our rule for that. Now, geometrically, you might also want to look at this. Let's say you have y equals x cubed. It looks a little bit like this. Now, y prime can be found just by using that rule, multiply by 3, let's bring the power down, multiply by x to the 1 less power, so that's 3x squared. And you end up with a parabola and a cubic function. And the claim is that the slope of 3x or x cubed is always positive, except for when it's 0. And I think that we can see that. If we know that 3x squared is always positive, except for when it's 0. And if we look at this graph, it's increasing from left to right. So if the function is increasing, that means if I drew my tangent lines, all of them are going to be increasing as you go from left to right. So that means they're going to have positive slopes. Here, we're going to have a tangent line with a slope of 0. Over here, we're going to have a tangent line that's positive again. Here, the tangent lines have a very large positive slope. And then as we get closer to 0, those slopes decrease. So our slopes go from very large and positive to very small and positive until they get to 0. And then over here on this side, we've got a small positive slope, a larger positive slope, a larger positive slope, and a larger positive slope. So the slopes get larger and larger. So the 3x squared makes sense as we get farther away from the origin. That's just sort of an intuitive way to look at the relationship between this x cubed and its derivative 3x squared. All right. Now, here's a rule that is, I think, intuitively obvious. The derivative of a sum of functions is just the sum of the derivatives. So if we know the slope of this function and we know the slope of this function and we add the slopes, add the functions together, the derivative of the sum is the sum of the derivatives. You just add those pieces separately. And if we were happen to be subtracting those functions instead, if this is f minus g, and we were taking the derivative, we'd get f prime minus g prime. So if we've got y equals 3x and y equals x squared, and we add those together to get y equals x squared plus 3x, which is going to look roughly like this. The derivative of this comes from taking the derivative of this piece and the derivative of this piece. The derivative of this piece requires us to use the power rule. So we bring that exponent down, multiply by x to the 1 less power. So we get a 2 times an x. And then the derivative of a constant times x is just the constant, because it's the derivative of the line y equals 3x. It's just the slope of the line, which is a 3. So the derivative looks like this. And then if I graph y equals 2x plus 3, it looks roughly like this. Now when x equals -3/2, the function is 0. And notice that the parabola x squared plus 3x has a horizontal tangent line down here. So if I look for the slope at that x value, the slope is 0. And then to the right of that, the slopes are positive, and they get increasingly positive the farther we get away from x equals -3 divided by 2. So they're positive, but they're increasing. So the slope is getting larger and larger and larger. Over here, I've got slopes that are small in magnitude, but negative. But the farther I get away from that x equals -3/2, the slopes increase in magnitude. So the function or the slope values are all negative values. The y prime values are negative, and they get more and more negative as we get farther and farther away from x equals -3/2. So hopefully that's intuitively obvious to you. But in practice, when I'm taking the derivative of a sum, it's just the sum of the derivatives. Take the derivative of this piece and the derivative of this piece using some of our rules. Now this one says the derivative of a constant times a function is that constant times the derivative of the function. To me, that's obvious. If you multiply a function by 4 or 3, it's just 4 times or 3 times taller than it used to be. So if I'm taking the rate of change, well, that's going to be 3 or 4 times larger than it used to be as well. Here's a very simple example. If y is equal to 3x, or excuse me, if y is equal to x, and I multiply that by 3, I get y is equal to 3x. So I've taken all the y values on this graph and I've stretched them vertically. I've made them 3 times taller. So they look like this. Then if I take the derivative of 3x and factor out that 3 according to this rule, and that's just 3 times the derivative of x. And the slope of x is just 1. So I end up with 3 times that 1, which is 3. And I think that's sort of intuitively obvious. We can apply that rule to polynomial functions as well. So let's say you have the derivative of 10 times x to the 4th. That's going to be 10 times the derivative of x to the 4th. So we get 10 times derivative of x to the 4th, which comes from bringing that exponent down, multiplying by x to the 1 less power, and then simplifying. 10 times 4 is 40. And so we've got that right there. So those are some very, very basic rules, basic differentiation rules. We've got a lot of other basic differentiation rules as well, including derivatives of trig functions, derivatives of exponential functions, derivatives of logarithmic functions, and we'll use the product and quotient rule as well. We'll have derivative of a product, we'll have a rule for that, and then we'll have derivative of a quotient, we'll have a rule for that, and then eventually we'll have derivative of a composite function, called up the chain rule, we'll have a rule for that. But this is it for our first set. In the next video, we'll talk about the derivatives of exponentials, logs, and maybe the trig functions. I'm actually not 100% sure about the order, but we'll make sure to cover all of that before we get into applications of the derivative. It's not just slope, there are lots of real-world applications, especially applications to physics. So we'll do that in another video.